3D printing with metal is one of the most exciting, fastest growing, and evolving areas in modern manufacturing. And if you're curious about how it works, where it's used, and why it's not just a cool gimmick, but a full-blown industrial tool, you're in the right place. I'm Sean with Evology Manufacturing, and if you've ever wondered about 3D printing metal, you're in the right place. Let's start with the basics. Metal 3D printing, also known as metal additive manufacturing, is the process of building metal parts layer by layer from a digital file. Unlike traditional machining, which cuts material away from a solid block of material, additive builds parts up, only adding material where it's needed. Not only is this faster for low volume quantities than traditional subtractive manufacturing, it opens up entirely new ways to design and build things that were previously impossible or impractical in one piece. There are several different types of metal 3D printing, and each one of them has its own strengths and ideal use cases. When it comes to metal additive manufacturing technologies, we can group them into three major buckets. Those buckets would be powder bed fusion, directed energy deposition, and then almost a catch-all bucket for these cool, awesome miscellaneous technologies that are a little bit less mainstream. Let's take a deeper look at each of these technology buckets for just a second. Starting off, let's talk about powder bed fusion. This is where your more traditional technologies are going to live. Powder bed fusion works by brushing a very thin layer of metal powder, then using an energy source like a laser or an electron beam to weld those layers together microscopically. Layer thicknesses can range from 20 micron all the way up to 120 micron plus. That's the thickness of the powder that you're spreading. It all depends on laser powder and gas flow and a whole bunch of other different factors on what layer thickness you can use. Binder jetting is somewhat of its own category. While it is a powder bed, the fusion is achieved by applying a binder to the metal powder. Either way, the name of the game here is layer by layer production. As the build plate lowers, the part is built up into a green part, meaning not cured. The biggest difference between binder jet and DMLS is the green part needs to be sintered to remove that binding agent. A thermal shrinking happens during this debinding process, which is difficult to simulate and predict accuracy on how much each feature of that part is going to shrink. Also, the density of these parts is lower than DMLS. These powder bed technologies are great for complex parts as the metal powder helps create a support around the part. For binder jet, you really don't need to print additional supports. For DMLS, you do. Let's change gears here a little bit, and the next bucket of metal 3D printing technology is going to be DED, or Directed Energy Deposition. DED works by depositing and fusing material using a focused energy source, out in the open, not in a powder bed. You can use a source like a laser, electron beam, or plasma arc. Blown powder and wire arc technologies are very common here. However, our friends over at Titomic have found a way to kick this one up a notch with their Kinetic fusion technology. This wicked cool technology uses metal powders blasted at a supersonic speeds, causing the material to fuse to substrates without lasers or arcs. This makes it a great option for parts that require several material types or are sensitive to heat or just need a lot of material deposited very, very quickly. Finally, we've got the last catch-all group of technologies simply known as others. Things like MELD or ultrasonic technologies live here. These technologies don't quite align with the other two buckets, but are still incredible technologies that serve a very specific purpose in the market. There is a ton to talk about with this bucket of technologies. So let us know down below in the comments if you want us to do a more in-depth look at these technologies or any of the ones we mentioned further up in this video. So now that you've got a feel for these core technologies, let's talk about what makes metal additive manufacturing so powerful. Design freedom. Because of how these processes work at a fundamental level, you're not limited by traditional tooling or subtractive processes. You can create shapes and internal structures that just are not possible in a single part with subtractive methods. Things like lattice structures for lightweighting, conformal cooling channels and injection molding tools, and optimized geometries for airflow or strength to weight ratios. That's a huge win for engineers who want to reduce weight, improve performance, or consolidate multiple parts into just one. Which brings us to Formula One. If there was any industry that lives and dies by weight savings, being compact, speed, and innovation, it's Formula One. Teams like McLaren, Mercedes, Ferrari, and a number of others are using additive manufacturing across their development cycles. They're not just printing prototypes, they're printing race-ready components that go onto the car week in and week out. Think titanium brake ducts, complex suspension mounts, intercoolers, and lightweight aerodynamic parts that are iterated and tested in real time. One of the biggest advantages F1 teams get from metal printing is speed to track. If a car underperforms on Friday practice, the design team can print a new component overnight and have it bolted onto the car by Saturday qualifying. Traditional manufacturing just can't move that fast. Additive technology gives them a way to rapidly test, refine, and deploy these upgrades without sacrificing strength or performance. And with materials like titanium, Inconel, and aluminum alloys commonly used in motorsports, metal 3D printing delivers on both the mechanical and logistical demands of the sport. Outside of racing, the same benefits apply to aerospace, where every gram counts and part consolidation can reduce failure points, fasteners, and even the number of inspections required. In modern medicine, additive manufacturing allows for patient-specific implants, custom surgical tools, and even porous structures that promote tissue integration. In the defense industry, it is a game changer for field repairs, lightweight armor, and component life extensions. Now, metal 3D printing isn't magic. It takes some serious engineering knowledge, process control, and post-processing to get from CAD to a finished functional part. In all of the technology buckets, you need to think about orientation, support strategies, thermal distortion, surface finish, and much more. Depending on the tolerance, parts might require post-print machining, heat treatment, or surface finishing to meet final tolerances and drawing specifications. So while the design freedom is huge, the learning curve and technical demands are real. But with the right expertise and the right equipment, it's absolutely worth it. At Evology, we work with companies across all industries to help them navigate this space. Whether you're prototyping a new component, looking to scale your supply chain, or just looking for some help taking your projects to that next level, we've got a full built-out ecosystem of technologies to get your parts from a digital file to physical reality. Metal additive manufacturing is here to stay, and as the technology matures, the costs continue to drop, the material options continue to grow, and the performance edge becomes impossible to ignore. So whether you're an engineer, designer, or just someone fascinated by the future of manufacturing, this is the moment to get involved, because once you start printing metal, you'll never look at manufacturing the same way again.